Hello, my name is Dror Regev. I will be giving this tutorial about stability and especially in the respect of negative resistance model of stability. This tutorial will serve us later on in understanding stability of LNAs, and it is part of the LNA tutorial and the seminar of RF CMOS design. So to give us some motivation to understand stability issues and the negative resistance model, we just need to understand that if we have a simple LNA and we do careful design, we will get the gain and we will get the low noise, and the system will be happy. However, if we will not be careful and we will not take care of the stability and will not understand stability issues, we will find that in time domain our LNA will generate such oscillations, and it will not be useful at all. So it's not functional. So we must understand stability. When we talk about negative resistance model, we still need to understand what negative resistance is, because it's not physical to find negative resistance in nature. In passive devices, we know that in active devices we can get negative resistance. And negative resistance will be the case where the current will be increased when the voltage is reduced. So it's very simple definition. We can use it just to picture what negative resistance looks like. And of course, it will be only available in active circuits because there's no negative passive resistors. Okay, stability and negative resistance model. What this model is telling us that we can take an amplifier and really split it to two parts. One part will be an active circuit, okay? And we will look at this as a load, and it will have some impedance of R load plus 1 over S C load, assuming that this active circuit will be capacitive. It's a good assumption because we know the transistor has a capacitive CGS input impedance. And then we will have the other part, which will be called a frequency determining circuit. And we will just choose a node between these parts. It's sometimes arbitrary, so we usually do it in the most simple way to analyze the circuit, okay? But this is a classic division of active and frequency determining circuit. And soon we will see what relationship between these two parts can support stability or can support oscillations that may be needed when we design oscillators. Okay, so now we see our amplifier with the node and the active part and the passive part, which is frequency determining, and we can look at conditions for oscillations in such circuits. So for oscillations to start, we can see here on the left, we need that the sum of the source resistance plus the load resistance, this sum should be lower than 0. So one of them at least must be negative. And we also need this other condition, 1 over CL needs to be higher than RS plus RL squared over 4LS for oscillations to start. So these two conditions are necessary for oscillations, but not always sufficient, as you can see in this reference below. However, at steady state, these will be the conditions to maintain oscillations. So the sum of the two resistances must be 0, and and SL plus 1 over SC needs to be equal 0. And so this will be the oscillation frequency, which is a very known result. F will be 1 over 2 pi square root of LC. And if we want to know what will be the frequency that the oscillations will start with, we can find the term here, and we will understand it in the next slide. In order to better understand the conditions for oscillations to start and the conditions to sustain oscillations, we can look at the same circuit model that we have shown before, and we will look at the characteristic equation of this negative resistance oscillator. And so this is the impedance of the source, this is the impedance of the load, the active part, this is the frequency determining part. And basically, if we want to equate it to 0, and if we assume a second order system, then we will get this equation that the second order polynomial equals to 0. And it is very simple to find the roots of such a polynomial. So if we look at the imaginary or complex roots of this polynomial, we will find that S12 equals an A plus minus JB. And the basic necessary requirement for oscillations is that these poles will reside in the right half plane of the Laplace plane. And so if we have such roots and A is positive, the resultant impulse response GT will be from the form E to the power of AT, where T is the time, A is this factor right here, multiplied by cosine of B times the time, which is just a simple multiplication. The two imaginary parts actually cancel each other, and we are left with this response. If we have a pair of complex poles, such as A plus minus JB, the resultant impulse response GT would be a constant times e to the power of AT multiplied by a periodic cosine. However, if this A, okay, is positive, then the function will be exploding, and this is how we define an unstable circuit or system. Of course, in reality, it cannot explode, because when the transistor will saturate, this exponent will become 1 as A will become 0. But at the beginning, when the oscillation starts, this will be the equation. And if we just now solve for the polynomial that we have here, we find the two roots, then we get these two roots right here. And if this exponent is negative, so if the sum of the two resistances is negative, because we have a negative sign in front of this term, the whole term will be positive, and then we will get this behavior. So we just need to make sure that the sum will not be negative, as we mentioned before, and this explained the condition we showed before. And again, we just now we can put these poles into this expression of the impulse response, and find out again that the resistances should be positive for not getting oscillations. If they're negative, we will get this behavior and we will get an unstable system. In this tutorial, we have talked about the negative resistance model. Important part is that we need to make sure when we design a circuit that at any node that we will choose, the sum of the resistances that will be seen from this node to both different directions, this sum will be always greater than 0. Otherwise, potential instability issues may occur.